Okay, so let's pick up where we left off in the last video. We have this function f of x, and we have a secant line through the beginning and the ending points on some interval, closed interval a, b. We can write the equation of the secant line just in terms of f of b, of a f of a, and b f of b, which we did there. Then we introduce a new function g of x, which is the difference between f of x and that secant line y. And you should notice that now that function g of x, by making it the difference between f of x and y, starts at 0 and ends at 0. And so now we have a function where the y value for the left-hand endpoint and the y value for the right-hand endpoint are the same. Furthermore, by the definitions of continuity, since f of x, the original function, is assumed to be continuous, and the secant line is a line which is also continuous on the closed interval from a to b, so g of x is going to be continuous on a to b. And since both f of x and y are differentiable everywhere, so f of x minus y will both be differentiable, or g of x will be differentiable everywhere on that open interval from a to b. And finally, we have that g of a is equal to g of b, which is 0. And we can see that in a little purple diagram there. By defining g of x as f of x minus y, it starts at 0 and it ends at 0. So now we have a new function that satisfies the criteria or the conditions of Rolle's theorem, so we can state then that g prime of c has to equal 0 for some value c on that open interval from a to b. Now what do we do with that? Well, we're going to go back to our definition of g of x, which is f of x minus y, and we're going to take the derivative of g of x. And maybe that can be easiest stated as f prime of x minus y prime. But remember that y is just the equation of the secant line, and its slope is its derivative, and its slope is f of b minus f of a over b minus a. And those are all constants. A, b, f of a, f of b are all constants there. And so we have g prime of x is equal to f prime of x minus the quantity f of b minus f of a over b minus a. And g prime of c then is going to be, g prime of c is f prime of c minus f of b minus f of a over b minus a, and that has to equal 0 as we stated above. And then all we simply have to do is move the slope, the f of b minus f of a over b minus a, over to the right side, and we end up with f prime of c is equal to f of b minus f of a over b minus a, which is the mean value theorem. Alright, so let's go back to this. We have a function that is continuous on a closed interval. We draw a secant line through the endpoints of that continuous function on that closed interval. We make the equation of the secant line. We define it in terms of a f of a and b f of b, and it turns out to be f of b minus f of a quantity times the quantity x minus a plus f of a. Then we created this new function g of x, and g of x is just the difference between f of x and y. We can see that that starts at 0, it increases, and then it comes back down to 0 at the second endpoint. So g of x is f of x minus y. It starts at 0 and it ends at 0. G of x is a continuous function on the closed interval because both f of x and y are continuous, and g of x is differentiable on the open interval because both f of x and y are differentiable on that open interval. And since g of a is equal to g of b is equal to 0, g of x starts and ends at 0 on that closed interval. Therefore, it satisfies the conditions of Rolle's theorem, and g prime of c for some c on a to b has to equal 0. So we go back to our g of x definition and we take the derivative of that to find g prime of x. That's just f prime of x minus y prime, where y prime is the slope of the secant line, which is f of b minus f of a. We evaluate that derivative at c, set it equal to 0, and we have f prime of c is equal to f of b minus f of a over b minus a, the mean value theorem.